Yeah. Okay, so how was the midterm? So good, bad. Anyone who is saying bad from his or her perspective.
Is
or
the
point.
possibility of a curve in the big? What's that?
No. Because I announced in the syllabus that we will use the absolute grading. So everyone will get what he or she deserves. Okay. Okay. So today I am going to first discuss some questions of the midterm. The solution of the exam is already released. It is available on the syllabus page. You can have a look. For those questions which are like theoretical, I'm not going to discuss them here. You can check the solution. Okay, so question 5. So it was about drawing the process tree for this given code. And let's see how it works. So if you have this code, I'm executing it. So let's say that this is the process one, right? Initially, there is only single process. When I invoke when you execute PID is equal to fork, at that time point, the whole address space is duplicated, which basically means that exact same copy of the process is created. So we have another process now numbered as 2, which is the child of the process with ID 1. And now both processes continue executing from the same instruction or from the same statement. So for the parent process, this if PID statement is equal to 0 is false, right? So the next instruction or the next statement to be executed is this one. So it's stuck in an infinite loop. For the child process, the condition is true. So it continues executing. And the next instruction it has to execute is fork. So when this fork is executed, an exact copy of this child is also created, which means that you have another process with ID 3, which is basically the child of the process with ID 2 and grandchild of the process with ID 1. So again, both process 2 and 3 continue executing from the same point. Sorry. So for the child process, the condition is true, so it gets stuck in the infinite while loop. For the parent process, the condition is false, so it continues to the next statement after the while, which is again a fork. So in this case, since this is now stuck, I am simply removing it for the purpose of animation. And then when this process continues executing, so when it executes the fork, it again creates another process. But this process is child of the process with ID number 2. I'm giving it the ID of 4. And when it executes the conditional statement, it is true, so it gets stuck in the while loop. When it executes the conditional statement process with ID number 2, the condition is false, but then even after that, there is an infinite loop, so it gets stuck there. Okay, so all the processes, they keep executing an infinite loop. And this is the solution on the right side which you have. Okay. Any questions? Yeah.
So after the 3, like on the
after the 3,
like after that while loop, would it not create another child within?
Because it will never exit the while loop, so it will, yeah. So the control flow will never exit the loop, so nothing will happen. Right? Any other question? By the way, before the exam, like 2 days before the exam, I released an animation of about how fork works, and I made an announcement. I don't know whether you were able to see it or not, but it explains how fork works. Okay, so question number 6 here. You were supposed to write the output of the following code snippet. Basically the same thing. The only difference is in the, like in previous question, I asked you to draw the process tree, and here you just need to print the output. But the thing is, the mechanism is same, right? So here again, let's say we start executing, and initially we have only a single process, which I'm naming as process 1. So the arrow indicates both the point of the execution of the process and also the ID of, let's say, that process. So z is equal to 3 plus 1 plus 2 is equal to 6, right? And then next statement to be executed is fork. So when I execute the fork, the whole process is duplicated. So I now have another process to which I'm giving the ID of 2. Now both will execute the conditional statement. For the parent, it is false. For the child, it is true, right? So, which means that for the child, the next instruction to be executed is within the body of the conditional statement. And for the parent, it is after the conditional statement. So what happens here that when parent executes the statement, it increments z to 6 plus 1 plus 2. But remember, both of them have their own independent address space. Initially, the address space was same. So the changes made here doesn't affect the child process. Okay. So, and the child at the same time executes that printf statement. And so on the output, you see z is equal to 6. Now the cursor actually is just indicating what is the next instruction to be executed, a statement to be executed. So in the next statement, when we go move to the next statement, the parent executes printf. So actually, since for the parent, the z was equal to 9. So on the console output, you will see z is equal to 9. And then it returns 0, which means it's terminated. And then after that, the child executes z is equal to z plus x plus y, which is equal to 12, and then it prints f, and you see the output. Okay. Any questions?
So on this point, what happens if the parent terminates before the child reaches the quit state?
Okay. I'm assuming here that if the parent terminates and the child is still there, so the kernel or the operating system doesn't kill or terminate the child process. But if you assume something different and you have stated your assumption, then I'm fine with accepting your different output, provided that you have stated your assumption. Okay. Any other question? No? Okay, question number 8. Yeah, it was about Amdahl's law. So consider a program with 50% of its code being parallelized while remaining 50% being serial. That is not parallelizable. Using Amdahl's law, what maximum speed up can be achieved while running the program on 2-core platform? What about 16-core platform? You must do the calculations to get the score. I think it was straightforward, right? So you have S is equal to S, which is the serial part, right? 50%. So 0.5. The parallelizable part, which is 1 minus S. So it is also 0.5. Number of cores is 2. You plug in the values in the Amdahl's formula, and you see this result, 1.33. And same for 16 cores. The only difference is that now n is equal to 16. So when you plug in the value, you see 1.88. The only thing, I mean, what I wanted you to realize is that if you, just by increasing the number of cores, everything else is same. So since now the work is divided among 16 cores, as a result, you have the denominator is smaller. So when denominator is smaller, the whole result is big. So your overall speed up is higher. Okay. Any questions? Yeah, go ahead.
Is the serial part?
Yes. So S is serial part, and whatever is left is the parallel, which is 1 minus S. Anything else? Okay. Question 10. What is the output of the following code? I mean, it looks like the code is big, but it was very simple, I guess. So I'm not going over the code. You have already seen it in the exam. So let's say we start executing the program. So there are basically 3 threads. One is the main thread, and then 2 more threads are created by the main thread. So let's say we are executing, the control is at this point. So 2 threads are created, which I'm naming as, sorry, here I should have written A, but anyway, assume it is A. So it creates 2 more threads, B and C. And now both threads, they execute the same function, thread function. The only difference is that they are getting the different IDs, one thing. So the first thread B is getting the ID equal to 1, the thread C is getting ID equal to 2. And the other thing is that here we have written thread local, into which means that both threads have their own local copies of private copies of X, Y, and Z, which means they are independent. So the changes made by one thread are not visible to the other thread. Changes made over X, Y, and Z. Okay. So when these threads execute, so I mean, you can simply do the math, right? 1 plus 1 plus 1 plus 2 plus 3, and on the other case, 2 plus 1 plus 2 plus 3. So you will get 7, 8, or 8, 7, right? Because we are printing on the output on the screen, which is an output resource. So it is like given to one thread at a one time, which the printf is serialized, the console is serialized. So if the first thread gets let's say the threads are scheduled and executed in such a way that thread B gets the control of the console first. So it will print 7 and then it will print 8. But let's say there is another situation where I run the same program again, and this time thread C gets the control of the console first, and then thread B. Then you will see on the output 8 and 7. So either one is correct. If you have written 7, 8 or 8 and 7, it's fine. Any question? No?
Where are you getting the my ID equals 1 if it's stuff that's here?
I'm passing here the value of the ID, and
yeah, I saw
so
that.
it is copied into the address of this is passed to the thread function. So then you dereference it, right? Okay. So done with the exam. So we can now continue our lecture of today. So what we were talking about before our midterm exam, we were basically talking about multi-threaded processes, right? So if we have multi-threaded processes, what was, if you remember, what was the motivation of having the multi-threaded processes? We wanted to increase the performance by keeping our CPU utilized all the time. So basically to increase the utilization of the CPU, right? And also to increase the responsiveness of our processes. So let's say we have an example where we have a process A such that this is the timeline for the execution of the process A. Let's say it first executes, which means it uses the CPU. And then it starts waiting for some IO. And when it is done with the IO, then it gets back and it is allocated the CPU and it starts again executing, and so on. So basically, which means that the lifetime of the process is consisted of 2 types of things. One, CPU execution and IO, right? So when it is doing IO, it is not using CPU. When it is using CPU, it is not using IO devices, right? So which mean, so these are known as like CPU burst, where you are executing the CPU instruction, and IO burst, where you are waiting for the IO doing the input or output. Okay. So when you are using when you are executing, the IO devices are idle, and when you are using the IO, when you are inputting or outputting some data, so your CPU is idle. So which is basically the wastage of time for both, like from the perspective of both CPU, both are resources, right? CPU is a resource, IO devices are resource, right? CPU time and IO device sharing. So let's say now we have another process which also has the similar pattern. Like it also performs some CPU execution and then waits for the IO and so on. So here we are basically from the CPU perspective only, we are wasting the CPU time, right? So how we can solve this problem? Our target is like, we want to keep our CPU busy all the time. So how we can solve the problem? No, someone else. Someone else. Yeah, go ahead. No. Okay. Oh, yes, go ahead. Yeah, just keep switching between them, right? Interleave them for the CPU execution. So if you do that, so like process A is when process A is executing, after that when it is done, and now process A goes for the IO, you can allocate the CPU to the process B, right? And so on. So if you look from the CPU perspective, I mean, this is the ideal case. I mean, try example. This is now how in real world it will work, but this is what we ideally want to achieve, that our CPU is never sitting here. And okay, here in this diagram, I have shown only from the CPU side, from the CPU perspective, but you can consider a similar kind of situation even from the IO device perspective. Like for example, when process A is executing, process B is doing the IO. And when process B is executing, process A is doing the IO, right? So IO devices also remain always occupied. But again, that is always an ideal situation, right? But this is what we ideally want to achieve, right? So this is the motivation behind having the multiple thread and then successfully scheduling them such that if there are no multiple threads, you cannot keep the CPU busy all the time. And if there is a case that you support the multiple threads, but then you are not able to schedule them, you have the thread model, you have the abstraction of threads, but you don't have any idea or any mechanism to schedule them, then even then you cannot use the CPU for maximize the CPU utilization, right? So you need to have support for both kind of things, thread implementation and also the thread scheduling. Okay. Okay. So I started talking about thread scheduling, but we never asked the question, what is scheduled for? Why I'm scheduling the thread? Why I'm not scheduling the processes? So the question we need to first ask that what should be scheduled for execution on the CPU? Should we schedule the thread or processes? And also, if let's say I say threads, then which threads? User level threads or kernel level threads, right? So what is your answer to first question? What is scheduled for execution on the core, on the hardware? Thread or the other process? Yeah.
Using threads,
What's the reason?
because threads are like the smallest schedulable unit. And so they want to
Yes.
like maximize utilization. You want
Yes.
to have the most like unique disjoint things that we can schedule. They're also the smallest.
That's correct. So remember we said when we started talking about, we said the thread is the basic unit for CPU scheduling or for allocating the core to for the execution purpose. Now, thread is like least how to say, finest granularity for execution. So finest granularity means you have more control, more flexibility, right? So that's why we use the threads for when we for the schedule. We schedule the threads, not the processes for execution. And which one of them, like user level or kernel level? So okay, I have given the answer kernel level, but the reason is, what is the reason?
The kernel is not aware of the use of threads.
Yeah, because remember, even if you have the user level thread, you have to map them to the kernel level threads, right? So kernel level thread is at the end of the day responsible for those user level threads. So kernel sees only those kernel level threads, not user level threads. So definitely, if kernel is responsible for scheduling, then it will schedule the kernel threads, not the user level threads, because those user level threads are like not visible to, they are managed by a kernel level thread. If it is one-to-one mapping, each user level thread is managed by a kernel level thread. If it is many to one, then there is a different story. But at the end of the day, your kernel level threads are responsible. Okay. So scheduler is a module of the kernel or the operating system which is responsible for selecting one of the ready processes from ready queue to execute. Remember, we in the previous one of the previous chapter, like chapter 3, we were talking about different states of the processes, right? So a process is in a ready state when it is not waiting for any IO or when it is not interrupted. Basically, it is waiting for its turn to get the CPU, right? So, but at a given time, it is possible that more than one processes they are waiting, they are ready, they don't need to wait for any IO, they are waiting for the CPU to be allocated to them. So it is like multiple candidates and one seat. So now what will happen is that you need to select one of them. So CPU scheduler is the module which is responsible for doing that job, okay? Yes, it is responsible for doing that job, but then based on what criteria? What is the selection criteria which you use for selecting one of those candidates? And also, let's say if there are like 3 processes, A, B, and C, and the scheduler has selected one of them, let's say A. So how long a scheduled process can keep the CPU? Can it like, until what time we should allow it, or should we not put any limit on a scheduled process to release the CPU? So about the selection criteria, we will talk about later. There are different scheduling algorithms which select one of the candidate processes based on certain criteria. And we will talk about them later. But now let's first talk about how long a scheduled process can keep the CPU. What is your answer? What are the options here? What are the possibilities?
For
Yeah.
a limited time jump,
Okay, go ahead. Okay. Go ahead.
just either keep it forever or just keep it down to a predetermined limited time jump.
Yeah, I mean, there are 2 obvious options. One, keep it forever until I'm done, or kick out that process which is designed the CPU after some threshold, right? So the first one, which is that the scheduled process voluntarily releases the CPU, that is when terminated or waiting for an IO. I mean, if process A is allocated the CPU, and now it is up to the process A when it wants to release. If it never wants to release, it will never. But let's say when it is terminated or when it needs to now wait for an IO, then at that time point, it will release the CPU. So this is like the naive approach or the first approach which comes to your mind, right? So this is easy to implement, but the problem with this is that it reduces the responsiveness. Like, for example, if I have 3 different processes, A, B, and C, and I allocate the CPU to process A, and let's say the execution time of process A is 100, execution time of process B and C are, let's say, 50 and 50. Now, these B and C, they will never get the chance to execute until the process A has completed, or by chance it has to wait for an IO, right? So which means that now my process B and C will always be waiting. And if I am a user and to me, it looks like that process B and C are very slow in execution. So if I want to interact with them, they will be very slow to produce any kind of output. Because basically they are slow in making the progress, execution progress. So this is known as non-preemptive scheduling, because once you are allocated the CPU, you are not kicked out unless you voluntarily release your CPU. You are not forced to release the CPU. The other option is that we schedule a process, but then that scheduled process is forced to release the CPU based on a condition. For example, let's say you allocate the time budget for every process, and if the time budget expires, the time budget can be, let's say, same for all the processes, or it may be different. Let's say 5 seconds for process A, 7 seconds for process B, 6 seconds for process C. But whatever time budget it is, If time budget is expired, then you kick out that process. Or maybe let's say the time budget is not yet expired, but another higher priority process becomes ready. So since it is a higher priority process, and if you are doing priority-based scheduling, then the lower priority process need to be kicked out, even when its budget is still available. So what do you think? What is the positive side of this one? Anyone else other than the first row? Wrong answers are also correct answers during the lecture. So go ahead.
What was the question again?
So what is the downside of this approach where we are forcing what is the positive side of this approach where we are forcing a process to release the CPU once it is scheduled based on some condition? Go ahead.
It gives other processes a chance to.
Yeah, so the other processes are not starving. So the issue is like, for example, if you consider, let's say, consider a situation where one process gets stuck in an infinite loop. Let's say the user wrote a buggy code, right? In first case, since the process never releases voluntarily, so what will happen that your CPU will be stuck, and this process A will be stuck, and all other processes will also be stuck. So there will be no progress. But here, if the time budget, let's say, is expired, so the other processes get the chance. At least all of the other processes, other threads or processes, they are able to make the progress. Here, by the way, for the purpose of CPU scheduling, I will be using the term of thread and the process interchangeably, which means basically the same thing. Because let's say you have a process which is single threaded, so it is a single thread, right? So it increases the responsiveness because other processes are also allowed to make the progress, irrespective of whether the process A in our example is stuck in an infinite loop or not. All of them are allowed to make the progress. And this is known as preemptive scheduling, right? However, there are issues with this one. This can create race conditions. For example, two processes, let's say we have two processes which are sharing the data with each other, right? And you have process A and you have process B, and let's say this is producer. We have talked about producer, right? And let's say this is consumer. This is shared data, shared memory area between them, shared among them, between them. Okay, so now let's say that this process A was producing some data. And during the process of producing the data, so let's say it has to produce, from our project, one example, it has to initialize first array of the matrix, right? So let's say this is the first array of the matrix. And it was somewhere here. So all these elements are initialized and remaining are not. But then the time budget for this process expires. So let's say we had 5 seconds for this one and they are now expired. And then the scheduler does what, that it kicks out this process. Suppose we have only single core. It kicks out this process and then process B is scheduled for execution. And let's say the job of the process B is that multiply the whole first row with 2. So it will start executing, but then the array was not yet fully initialized. So it will be operating on the uninitialized data. Here you have garbage, right? Here in these elements you have garbage, right? So the result which will be produced will be not correct. So as a result, what will happen is that you have the race condition, basically, which means that process B starts consuming the data even before it is produced by the processor. So basically the same thing which we have, I think, talked about in other lectures, that you need to synchronize the process A and process B, right? Yeah, go ahead.
So the time budget, is that like I assume we'll probably go over this, is that like dynamically change depending on what process is being scheduled?
Yeah, I mean, there are different criteria, or there are different policies. As I said, either you can allocate, for example, in round robin algorithm, what you can do is that you have the same time budget for each process. Another option is like, okay, I have the time budget, but then it is not same for all the processes. Maybe for those processes which are high priority, I allocate them more time budget. Okay. And then maybe there are some situation where I allocated, let's say, a time budget of 10 seconds to a process, and it was able to complete its execution before 10 seconds. Then I can allocate the remaining budget to the next second higher priority process and so on. So it is not like, a fixed thing. Okay. It is a parameter which based on the algorithm maybe is how it is changed depends on the algorithm. Okay. Okay. So also actually this issue is also an implication of the same situation where a race condition is created. Let me explain this one, and after that we can take the break. So since we are using the preemptive scheduling, it can potentially leave the kernel in inconsistent state. So again, basically it is the same. The basic reason is same. Let's say you have again process A, and the process A is executing and it's make a system call. So when it makes the system call, it is trapped into the kernel, right? Now, kernel takes care of whatever functionality needs to be provided by the system call, and let's say the kernel is executing this set of instructions or set of statements, right? And let's say that in between, when it is executing here, an interrupt arrives. Now, if interrupt arrives, kernel need to take care of this interrupt, right? So it executes the interrupt service routine, right? Now let's say that these instructions which kernel have executed before the interrupts arrive, they would be some kernel level data structure. Okay. And this interrupt when it arrives, but this was like, let's say there you are making some changes, but the data structure is not in consistent state. What is meant by not in consistent state? I will explain. Let me come back and then I will tell you what is meant by not being in a consistent state. So let's say you have the interrupt and then ISR need to be invoked. And let's say this ISR also need to update the same data structure. But this data structure was need to, let's say, read data from this data structure. But this data structure was not in the consistent state. Now this ISR will not work in the way how we want it to work, right? And by inconsistent data structure, we mean, let's say I give you a simple example. Let's say you have a linked list, A, B, and C. And let's say you want to insert another node, and let's say, let me simply name it D for the purpose of example. I have nodes A, B, and D, and I want to insert another node in this linked list, node C, and I want to insert in order, which means I want to insert it after C, after B, and before D. So how can I insert first? I mean, there are multiple ways you can do, but let's say first step I do is that I create this node C. I set its forward pointer pointed to D, and I set the forward pointer of B to D. Like these are two steps, right? And then this one is removed. And I'm updating it, so definitely it is removed. So 1 and 2, right? Let's say that I have updated 1, its forward pointer, but before I perform the step 2, the interrupt arrives. Here. Now this is my data structure, right? So what will be the state of data structure? A, B, D, C. This is not the correct linked list, right? So C is there, but C is not reachable from this point, from the root. So now if my interrupt service routine need to access, let's say, data, read some data. So what it should read? Should it read C or should it after the what should like what is the right child of B? Is it D or is it C? Right. So this is the issue. So again, the problem basically is same. So which we had in this producer consumer thing, that here we are doing something and in between we are interrupted before we have completed the operation. Just like here, we were interrupted before we had completed the initialization of the first row of the matrix. Right. So here again we get interrupted. So what we can do is again the same thing. Maintain some kind of synchronization mechanism which doesn't allow you to be interrupted before you have completed the operation what you are performing. So do some kind of synchronization mechanism, for example, locks, which will prevent inconsistency in this particular case, or even like in case of the producer and consumer, it will solve the problem, right? Any questions? Okay, so then we can have a 10-minute break, and then after that we can continue.
I have a question that you want over for class time. How does the OS or the kernel, I guess, perform on garbage collection in that situation? Where now we have C pointing to D, but we can't reach C. So it's just taking up memory and we can't do anything.
Yeah, so what does the OS do is that whenever you allocate the memory, like for example, in this case, you are allocating the memory for node C, right? So whenever you allocate the memory, what you can do is that you can maintain the record of like what segments of the memory are allocated, one thing. Second, if it is allocated, are there any pointers pointing to that memory location, right? So what you do is that after every certain amount of time, what you can do is that you can check the list of all those memory areas which are allocated, and then you check that whether there are any pointers pointing to them, which is known as reference counting.
Okay, that's
So if there is no reference counting on a allocated memory, it means it is not used by any part of the code.
okay.
So which means this basically maybe the programmer forgot to deallocate it or free it. So now the OS or the kernel can assume it as a garbage and deallocate it and make it available for the next allocation. Yeah, this is like one basic approach.
How would that be different from like a mark sweep approach?
How it is different from?
From mark sweep garbage collection? Because I thought mark
I-
sweep was like when we go through all the things we can reach. And then we also have a log of all the things that have been allocated.
Yeah.
And we cross-reference them and then the things that we
Yeah,
can't reach.
this is basically the same thing, mark
Okay.
and sweep. We are reference counting,
Okay.
comparing whether you have a reference to your allocated memory or not.
Okay.
We're doing the same thing.
Well, thank you.
Okay, so I'm just right now looking at the responses for this, what was this survey about whether we should have project 2 and 3 as individual project or the group project. So there are like 7 students who said that they are not comfortable with the group projects. So we will have individual projects.
I got you some more white shots.
Huh.
Can we use this instead of the blue shot? It's just kind of hard to see on the black.
Oh, okay, okay, okay. Thank you.
There's also another one over there.
Okay.
I mean, not good. We're happy, sad, it's going on, I'm very happy, and is it gonna be different?
So, okay. So we were talking about scheduler, and we were trying to answer two basic questions, which was like, what is the criteria for selecting one of the candidate ready processes to be executed, and also once a process is scheduled, how long it can keep the CPU. Other than scheduler, we have another module, kernel module, which is responsible for giving control of a core to the process which is scheduled for execution. So scheduler has selected the process, but how the process itself, what is the mechanism for giving the control of the core to that process which is selected for execution. So for that dispatcher is responsible and need to do three things. First, it need to do the switch the context. Switching context basically means like kicking out one process and bringing in another process for execution. So here is how it works. Let's say you have process P0 executing, and then scheduler selected another process for execution. Now it is the job of the dispatcher to give the core to the second process, let's say P1. And how it works is that in order to do that, the dispatcher has first to save the state of the P0 into the process control block of the process 0, right? You know what is process control block and what it is used for, right? So you need to store all the related information into this process control block. And then you need to go to the process control block of the process 1 and then read all the data from there, whatever it is needed, and need to restore it in the registers. For example, you need to store the process, for example, what is this? PC, program counter. You need to store the program counter, you need to store the stack pointer, you need to know what files are open, so you need to know their file descriptors. Also, you need to know that what memory has already been allocated from the heap segment of this process 1, right? And you need to put all the local variables also into the registers. And then after that, only P1 can start execution, right? The time spent in like switching from the point where it is skipped out to the point where P1 is being brought in for execution. So this is known as dispatch latency, which basically is the time consuming saving the state of the process 0 and restoring the state of the process 1. The other thing you need to do is that the dispatcher need to do is that it needs to make sure that the execution mode is switched. So initially it is in user mode, execution is in user mode. And when you are doing before saving the state of the PCB 0 for process 0 to the PCB, you have this job can be done only by the kernel. So your dispatcher need to make sure that your kernel mode is set. And then it is set back again to the user mode. And third thing is that you need to make sure that actually this is incorrect. So let's say here the PC should be something like Y, and here the PC is something else. So it needs to make sure that the process which is now given the control of the core executes at the correct location. So let's say the last time when it was kicked out, its PC was set to X. Now this time when it is restored, its PC should also be set equal to X. So it should start execution from the same point where it was when it was like kicked out. Any questions? So that's the difference between scheduler and the dispatcher. the basic job of the scheduler is to select the process which needs to be given the core, but how it actually is given the control of the core is done by the dispatcher. Okay, so here are some commands which I wanted to share with you. So assume that you are running Linux, of some processes on Linux. So, and there are, let's say, is a process with the ID of 1516. Actually, if you remember in one of the previous lectures, we mentioned that if you go to cat process and you can list all the different process IDs running on the system. So let's say in my case, I had this process with ID 1516. So if you run this this command, cat process, and then the ID of the process followed by status, so it will give you something like this, like not only this output, there will be a long output, but at the end of that output, you will see two entries stating voluntarily context switches and non-voluntarily context switches, which basically mean that how many times this process 1516, how many times it voluntarily released the CPU. It was like allocated the CPU for execution, but then maybe it had an IO or it was like completed or something. So it voluntarily released 3 times, and 0 time it was like kicked out by force, or it was preempted. Yeah.
So how does the kernel distinguish between like a process that's run beyond its time budget because like in an error state or an infinite loop that needs to be terminated, and a process that's run beyond its time budget that just needs to continue finishing at a later point and perform a context switch instead?
How to differentiate between a process which is, let's say, stuck in a loop and a process which is not stuck in a loop, but
Just needs more time.
needs more time. So if it is not yet, let's say, terminated, so if you are in a loop, your state is not terminated, right? If you remember that process state diagram. But if you have actually completed your execution, your state will be changed. So based on the state, let's say when you execute the statement return 0 or exit, so then your state is changed to terminated. Now, if it is terminated, so you are in a different, but if in your while loop, you never execute exit or return, right? So your state is different.
But I mean, like two processes, it's like two different scenarios.
Yeah.
Neither of them are terminated. One will never terminate because it needs to be just, it's bad.
Infinite loop, let's say.
Yeah, and one is working properly, but the time budget was just not enough for it to finish what it needs to do.
Yeah.
And so this just needs to be like switched out and switched back in at later points.
Yes.
But this one needs to be terminated. Because if you were just to save that state and reload it again, it would always be stuck.
I think you're running into the halting point.
Can you like draw something on the board to let me understand what you're trying to say?
I'll try, not nervous.
Like pseudo code, for example.
Should I erase?
Yeah, you can.
That's fine. That's okay. Whatever. Did you get new erasers? Sure. You guys see that? And I just broke it. It's limited to two processes,
Okay.
I guess, right? I'm just gonna go a loop in this one.
So it is stuck in a loop, okay?
This one's bad.
Okay.
Right?
Okay.
So like we came into this process
Okay.
and we're never gonna come out, right?
Yeah.
Never gonna work. This one's just really long.
Okay. Yeah. Okay.
And let's say we're at this point
Yeah.
when our clock,
But
Runs
time
out.
expired. Okay.
right? So we need to save our state here so that when we come back, we go down through here.
Yes.
This one, if we were to save our state at this point,
Yeah.
we would never finish.
Yeah.
So this one should be killed
Why?
because it's never gonna work, right?
It will not be killed. It will be based on like your scheduling algorithm or what is your policy. If preemption is allowed, it will be, let's say, preempted, which means it will be kicked out, but it will not be killed. Both will be kicked out.
Right.
Yeah.
Question, is it maybe just like some other program's responsibility to handle that? And like,
Yeah, that is the job of the scheduler. scheduler is a different piece of code which is responsible.
Or like to handle like an incident, there could just be some other process that decides, okay, we're gonna do now.
No, if you that, I mean, in a typical case, what will happen is if you have these two processes. So in both cases, if you are here, let's say you will be simply kicked out, and when you are restored, you are again restored at this point, and you will keep executing when you come when you get your turn again, you will keep executing the value. Okay, and here again, same thing. You will be kicked out, you will be restored, but you will continue executing next instruction. Right. So basically, the mechanism is same.
So nothing will like take a look at that and be like, we shouldn't run this. Is that like a
If
user
you
responsibility?
have not some special mechanism, let's say, to handle the common cases where you select your maximum time which can be allocated, let's say I suppose that some maximum value. Let's say take one case like those.
Which is a different value from the time budget.
Yeah. So you have put an upper
Limited
limit.
time.
Yeah. So actually, in for example, in Linux, when you let's say you write a kernel module, you are writing some kernel level code, okay, and one of your thread is stuck. So it will give you a warning, or it will give you a soft bug that your thread is stuck, or your thread is not responsive. Yes, but it will not like terminate.
Right.
It will give you giving repeatedly those bugs, which is like a kind of indication that you need to fix it. Yeah. But also again, it is a kernel level decision. I mean, I don't know what the user want to do within that thread. So based on the functionality, is it a wise decision to kill it? Maybe it is an intentional while loop. Maybe it is not an intentional while loop. Maybe it is a bug. But the typical behavior is that when you are stuck, in both cases, your PCB will be saved and then restored. Now it is like in a kernel case, let's say you have an upper limit, and if you cross that upper limit, then maybe a warning is thrown. So that you can correct that. Any other questions? Okay. Okay, but by the way, here the non-voluntary context switches mean, let's say you had the time budget which has expired, so you were kicked out. And maybe here when 3 times you voluntarily release the CPU, maybe you were waiting for 3 IOs or something. Okay, there is another command, vm stat or virtual memory stat. So, and we can execute this and pass the arguments 1 and 3, which basically means that we want to run this command for 3 times. So 3 instances, and then the 3 instances are separated by 1 second. So when you run this on your machine, or in my case, I saw this output. But here we are interested only in this particular column of the output, which gives us the context switch information. So the first entry here gives you that on average, how much context switches have been performed since you have booted your machine. So since I booted my machine, on average, 1 context switch is performed per second. And then the remaining entries, like this is telling me that, okay, 40 context switches have been performed in the last 1 second, and the 33 context switches have been performed in the second prior to the last second. Okay, so basically the purpose of sharing this command is that this is not only some abstract things we are talking about. You can actually verify on your own machine that this context switching is happening here. Okay. And also when you will look, for example, at the output of this char process status command, you will have many other different entries. Some of them which are maybe meaningful for you at the time. Some of them are not. Maybe they will become meaningful for you at some later point when we make progress in this lecture. Okay, so the first question we had when we were talking about scheduling was like, what is the criteria to select a candidate process? So that to answer that, we need to ask another follow-up question, which is basically, okay, we are talking about the criteria. I mean, if we want to select a candidate, basically there must be a criteria for selecting the candidate. But then what is important for us? I mean, what criteria? There may be more than one, right? So what criteria is important for us, right? So which basically mean that what performance parameter is or critical for the application under consideration. So let me explain what it means. So there are multiple parameters which you can use to look at the performance of a particular system. Like what is important for you? Maybe one thing which is important for you is CPU utilization. Maybe you want to keep your CPU utilized all the time. You don't want to keep it idle at any given time. So if that is the most important thing, so this is like one performance parameter you need to look at. So I mean, there will be some algorithms which will be focusing on CPU utilization. Their objective or their target is to maximize the utilization, and based on that target, they will select one of the candidate ready processes in such a way that they can achieve the target. So let's say that we have two types of processes, CPU bound and IO bound. We have talked about these terms in one of the previous lectures. So CPU bound process is one which spends most of its lifetime performing computation. And IO bound processes are those which spend most of their lifetime in performing the input or output. Okay. So what do you think, which one of them will be good candidate for improving the CPU utilization? So I mean, definitely if you have all the available processes are CPU bound, so it's mean you always have some work to do, right? So if you always have some work to do, you can never release the CPU idle, keep it idle. But let's say if all the processes are IO bound, which means basically that there is very little work for the CPU to do. So most of the time it will be sitting idle, right? But then in ideal situation, we don't want only CPU to be utilized all the time. We want IO devices also to be utilized all the time. So a good mix of both, just like our motivating example, so that you can interleave or like switch between them. So you can maximize the utilization of both IO devices and the CPU. Also, maybe in some case of in some situation, you not only want to maximize the CPU utilization, but you also want to maximize the throughput, which is number of processes completed per unit. For example, let me give you an example. Like, let's say there is a database server and there are multiple clients and all of them are submitting the queries to the database server, right? And all of those queries are, let's say, taken care of by independent threads. So what is important for me? Not only this, that CPU utilization is high, but also from like user's perspective, how many queries I can complete in a given unit time, right? Higher the number of queries I can complete in a unit time, it means I can accommodate more clients, right? And I can make more money, right? So normally, if you have longer execution time per process, so it will result in lower throughput. And here is an example. Let's say you have two processes, A and B, and which are like duplicated. Like there you have 4 instances of A and 4 instances of B. They are exactly the same processes, just like you have seen in your example programs that you can launch multiple processes by just saying fork, right? So let's say you have 4 processes, 4 instances of process A, 4 instances of process B, and each instance takes 1 second to execute, right? So in total, they will take 8 seconds to complete, and the throughput will be the total. This is like, okay. Let me take back my wording. Let's say you have only two processes, A and B, and you are actually scheduling them on a single core. So you are allocating them the time in unit of 1 second. So you allocate first 1 second to process A, then next 1 second to process B, and so on. So in total, it takes 8 seconds to complete the execution of process A and process B. And as a result, when you will calculate the throughput, it will be 2 by 8, which is 0.25, right? So 2 processes are completed in 8 seconds. So now let's say that we simply reduce the execution time of the process. Let's say now I have written up the code of the process in a more efficient way, which means my code size is smaller, but I'm doing necessarily the same functionality, right? So, and let's say now I have 4 different processes, and each one of them takes 0.5 seconds. So now I can execute 4 different processes in the same amount of time, and my throughput will be 4 by 8, which is better than the previous one, 0.5, right? You have a question? Go ahead.
I think you just kind of touched on what my question was going to be, which is that like we have to change the code in order for it to be faster.
Yeah.
Right? So that means there are different programs that depending on how they're written will either take a short amount of time or a long amount of time. Which is then how does the scheduler kind of pick what jobs would be small jobs so they can get more jobs done?
Yeah. So actually the thing is like, first sub question of what you are asking. So it doesn't depend only upon code. I mean, this is a toy example, so I'm just saying code, but there are multiple factors. Like, for example, your process is doing some IO, and that IO depends upon some external factor. Let's say I need to press a key for that process to continue. So I don't press the key, it will take longer for that process to complete, right? So those are the other factors. Now, what was your question? How does the scheduler knows?
How does it know what's a small job versus a large job? So that it can schedule in a bunch of small jobs to get completed while also running maybe like larger jobs and concurrency in the background.
Yeah. So you need to like, there is no way that ahead of the time you can find out that how long the process will take to complete, right? Because it depends on, as I said, depends on many factors like size of the code. It depends upon if you are interacting with IO, then it depends upon the external factor. So you cannot like know in advance. So that's why the algorithms which we are going to see, they don't schedule the processes depending upon the execution time. They schedule the processes depending upon other factors or other parameters, which we'll talk about. Okay. So here, what I was just trying to say is that throughput, it is like what is the amount of the work you can do in per unit time. And in this case, the amount of work is the number of the completed processes. So longer the process, lower the throughput. Longer a process takes to complete, lower the throughput. Shorter the time it takes to complete, then higher will be the throughput. Okay. But then, I mean, these are some parameters, like, as I said, maybe as a user, I'm not interested in throughput. I'm interested only in CPU utilization, or maybe I'm interested in both of them, right? I want to maximize both of them. Okay, another performance parameter is lower turnaround time per process, which is basically means throughput is like, you look at how many processes have completed the execution in a unit time, and turnaround time is from the perspective of the single process, not from the perspective of all the processes, which basically means that how long it takes for a single process to complete, right? So let's say I'm one of the client in the same example. I don't care about how long it takes for your query to complete. I'm interested from my perspective only on how long it takes for my query to complete, right? So both are important. From like at the system level, throughput is important, but from the perspective of the single process or the single client, your turnaround time is important. So turnaround time is defined as the time for submission of a process to its completion. The point where you submit a query, the point where your query is completed, how long it takes. And in between, it can be anything. Like maybe it spends some of its time in turnaround time in execution, sum of time doing IO, some time waiting in the ready queue and so on. Total time, okay, from start to the end. So here, the turnaround time for our process A is 4 seconds, assuming each block takes 1 second. And in the second example, which we have already seen, here the turnaround time for each block, for process A is 2 seconds because each block is taking 0.5 seconds. Okay. Another performance parameter, which from the perspective of the system is that how long a process need to wait for its turn to be allocated the CPU. So remember that the scheduling algorithm, it cannot affect the execution or the IO time of a process. Why? Because execution time, the time a process spends on the CPU, it depends basically on the instructions you are executing. So there is nothing the scheduler can do to change those instructions. If they are there, they are there. You have to execute them. Similarly, if the code of the process is written such a way that it also includes some IO, then scheduler cannot do anything with that, right? So the IO also need to be performed. The only thing the scheduler can affect is the waiting time. The waiting time when a process is ready to be executed, but it is waiting for its turn to be allocated, right? So based on how your scheduling algorithm works, that waiting time is affected. So one performance parameter can be like for a scheduling algorithm would be like how much I can reduce the waiting time for a given process on average in the queues. And in case of the interactive processes, the processes which interact with the external world, whether it is a person or some other devices, so and the other performance parameter is response time, because if our process is not responsive, then it will be very irritating if it is a human person or a human being interacting with it, or some other devices which are interacting with it. So they will also become slow if the process is not responsive. So how the response time is measured, it is the time from submission of a request to the production of the first response to that request. Not outputting the request, but just producing the data. Displaying that data, for example, on the screen, it takes extra time, but for the data to become available in memory is a different thing, right? So let me just finish the slide and then we can complete the lecture. So typically what we want to do is that we want to maximize 1 and 2, which is CPU utilization and the throughput. So higher is better. And we want to minimize 3, 4, and 5. So lower turnaround time, lower waiting time, and lower response time. So lower is better. So they are not mutually exclusive, which means that it is possible that there is an application which wants to optimize all of them, or 2 of them, or 3 of them, depending upon the use case, right? So any questions? Okay, then let's stop here and see you next week. The quiz project 2 is released, right? And quiz 5 is released. Sorry, today is the deadline. Okay, okay. Thank you. Okay.